right, so the other one that you guys were looking at was this one that involved hitting rocks. Well, as parents were out at night, a Nazi kindergartner discovers the joy of hitting rocks with a baseball bat. He notes that some rocks go faster depending on how light or heavy they are. Maybe we say like how massive they are would be a more physics type term. How much inertia they have, right? The babysitter, who's a physics student, turns it into an experiment. She says, hey, well, let's measure the mass of each rock and then see what is its velocity. So they come up with this table, right? Oh, you guys see the more massive the rock, the slower at least the baseball bat? That should make sense, right? Because should be related to Newton's second law of motion. I think that's kind of where this is going, right? Actually, so this may be a combination of not just kinematic motion, but also unit 2 type stuff, right? Newton's second law of motion. On the grid below, plot the appropriate quantities to determine the effect of the mass of the rock on the rock's velocity. Right. Okay. So if you graph, just straight up graph exactly what they have. If you put velocity as your vertical axis because that's like the dependent variable, and mass on the horizontal axis because that's your independent variable. So you have velocity in meters per second up here, and you have mass in kilograms down here. Okay, that's what you guys got. Okay. And do you guys have a graph that looks like that, which is an inverse relationship? You guys came up with an inverse relationship, right? Right. So you guys ready to score yourselves? Now the whole thing is worth 15 points. So here's 3 of them. 1 point for just having plotted points. 1 point for having axes labeled with units, so velocity meters per second, mass in kilograms. And the 3rd point for the scale must fill half the boxes, right? I mean, that's a common AP thing. Oh, let's see if I have some extras lying around. I had them all out on the desk. Here, I think I got 1 extra. Oh yeah. Oh, okay. Okay, yeah, but you guys have to share them. Oh wait, that is no, that's not that. Okay. Yeah, so that's the last time I got. So you guys have to share with each other. Yeah, just put them all out on the desk, all the ones I had, except for that one. Okay. All right. So there's 3 points right there. Okay. Let's go on to next part. Since the original graph is a curve, right, inverse relationships more specifically, okay, linearize the original data. Yeah, this is a skill that AP wants you to do, and we've done so many times in this class. Okay. Fill in the data table below to linearize the data. Okay. Well, if you have an inverse relationship and you want to linearize it, you have to do a reciprocal at some point. Okay. And actually, I think that's all you had to do. You just do like 1 reciprocal and boom. Because sometimes you have to do reciprocal, and then you also have to square or square it. But this one, I think reciprocal would have taken care of the whole thing. So, yeah, here's the way they did it. They did reciprocal of the mass and the velocity this way. Although if you did it the other way, I think it would also linearize. Okay. So is this the original? Okay. Yeah. So if you just did the reciprocal of one of those, go ahead and give yourself a point. Okay. If you realize something to do with reciprocal. Okay. So here's 1 over the mass, and the unit would be 1 over kilograms if you went that way. Right. And then the velocity is the same. Okay. And then this is the graph they got from this. Okay. Velocity in meters per second, right? Because it has units, right? No naked numbers. You guys have units on these numbers, meters per second. Okay. And then mass in kilograms, same as before. Okay. And look at that. It linearizes. Just like that. Oh, what would have made you suspect that it would have linearized? Well, I'm thinking a combination of a couple of things. Maybe how about this? F equals ma. So acceleration is equal to force acting on mass. Right. Now this kid hitting the rocks is probably a pretty constant force. So it's basically a constant force. Right? But different masses produce different accelerations. Now the acceleration is just while he's hitting with that, which is like a split second. So what does that have to do with velocities? Well, I'm thinking something like this. V final equals V initial plus AT. And that'd be true. And if the rock basically starts from rest, maybe it's like hitting them from a T or just like top them up, so not moving that fast. This number is pretty much 0, right? Goes away. Okay. So then acceleration would be V final divided by the time interval so that it feeds in there. Right. So here's the velocity connection, right? So on the table, right, you got this as a function of this. What was the original graph? Right. Okay. So let me put this all together. Df over t equals f on m, or if you like, v final equals force times time divided by mass. Right. Oh, force times time. What's that called in physics? What's force times time? Oh yeah. Okay. It should not have been a square root though. Okay. Now, if you did 1 over v versus m, I think that would also linearize. Okay. Okay. But yeah, no square roots though. That's fine. Okay. Right. Yeah, you guys remember force times time is like an impulse, like a change in momentum, right? So yeah, just make a connection there. Guys, what time roughly are we talking about? We're talking about a few seconds. What were you talking about? A tiny fraction of a second. This is like the bat hitting the rock, right? This is like maybe like a few milliseconds or something. Okay, just remember that, right? Okay, so this is kind of like the full expression of the graph. Okay. All right, back to here. Or so on the graph, right? Okay. Now make the linearized version of the graph. There it is, linearized. Here's the points for this. Looks like 4 points they're awarding. 1 point for just plotting points. 1 point for line of best fit. All right, so you got a linear relationship. 1 point for axes labeled with units, so velocity in meters per second, 1 over mass and 1 over kilograms. Okay. And the last point for scale must fill up half of the boxes. So if you did everything like bunched a whole tiny quarter down there, that's not good. You gotta have a good amount of graph. Okay. Just make sure everybody's following here. You guys know this is not technically from AP, it's from a organization called NIMSI, but I mean it's pretty close to like something you might see. Right? They wouldn't square it exactly this way, but pretty close, right? All right, you guys good? Right, then these questions. Question 4, calculate the slope of the best fit line showing your work. Be sure to include units with your number answer, the slope of the line. So, okay, well, I guess we're picking up from the last thing. Would have been really good to do exactly what they did with like 1 over mass and then velocity, but if you did the reciprocal the other way, then I guess you've got a little bit different slope. But anyway, if you did the other, show hands. Did anybody do mass and 1 over velocity? Anybody do that? Ooh, okay, good. All right. So so we're all on the same page. Okay, so that'll help us out here. All right, so we've got okay. Did you guys come up with a 10 kilogram meter per second or something pretty close to that? Right, maybe it's like a window of options. So they might say like between like 9 and 11 or 9 and 12 or somewhere within that window. You guys come up with basically that number. Okay. So they got 10 and the unit would have been kilogram meter per second. Okay. Or maybe you have, what's the equivalent of that? Is that Newton? Hold on. Newton seconds is the same thing, I think. So if you had like 10 Newton seconds, I think that's equivalent. Right? Okay. So showing your work is the point and getting the correct answer is the point. Okay. Or here, let's look at it like from this point of view. Okay. So let me continue this. F times T over M is what I had. So velocity final is equal to F times T divided by mass of the rock. Okay. Or if you write it this way, velocity final equals force times time all times 1 over the mass. Right. Here's your y-axis. Here's your x-axis. And here's the slope of the line, right? The slope. Okay. So they got 10 kilogram meter per second. That's also called 10 Newton seconds. So either one of those would work. Okay. Question 5. Using the slope of the line in your graph, write the physics equation for velocity of the rocks based on the rock mass. Ooh, well, it's almost here. All you have to do, instead of F times T, you just replace that with 10 kilogram meter per second. Right? Wouldn't that be true? 10 kilogram meter per second. So I would do like the velocity of the rock is going to be 10 kilogram meter per second. Okay? That's like the kid hitting the rock with the bat, that's like the impulse that he applies to every single rock, regardless of its mass. Okay. Times 1 over the mass of the rock will tell you how fast it goes. So I would have done that right there. Okay, that looks good to me. Let's see what. Oh yeah, there you go. That's what I got. Velocity equals 10 kilogram per second times 1 over mass. Or you could have said velocity equals 10 Newton seconds times 1 over mass. Right. How they score this thing? They say velocity of point, slope of the value in units per point, and 1 over mass of the point. Okay, so if you had the y-axis as velocity, you get a point. If you had the slope with a number and units, you get a point. If you have the x axis as 1 over the mass, you get the third point. Okay. All right, guys good? Okay, last question. Assume the youngster is able to continue swinging with the same gusto. Ooh, maybe the physics term for that would be applying the same impulse, right? The 10 Newton seconds, same impulse. Okay. What would be the velocity of a 1.5 kilogram rock? Okay. Which I think was like on the heavier end. Yeah. So like his heaviest rock was a kilogram. A kilogram is here's a kilogram right here. Ooh, looks like your largest lab mass. So what if it was like 1.5 times this? Right. So same kid, same bat. Well, you guys have an equation for it. Let's figure out right here. If you plug in 1.5 kilograms right here, you guys see the kilograms can cancel? 10 kilogram meter per second times 1 over 1.5 kilograms. The kilogram cancel. Okay. What is 10 over 1.5? 6.67. 6.67, and then the unit is meters per second, which describes the speed. That's all good. Okay. They usually don't even want that much precision. They might take 7 or 6.7, but yeah. But they don't. I've seen them not count off for like too many digits. So if you have like 3 digits, that's probably the safest thing to do. I think. I don't know. Okay. So, here's what they got. 6.7 meters per second, a number in a unit. So the magnitude, 6.7 is a point, but the unit is also important, right? Meters per second, because it's 6.7 what? We're talking about miles per hour, meters per second. Okay. So yeah, there's all 50 points. All right, guys get that? Ooh. Okay. Well, I did want to show you guys some optics demos, but we're gonna have to say that for a different day because we got about a minute left. So throw all that stuff in the gray tray, and that'll have to be a wrap on this week. On Monday, we'll do maybe classrooms and have that done by then.